Hello students, today we will explore chapter 9 hydrocarbons. So this will be our theory part 15 in which we will cover NCERT section 9.5.3 and 9.5.4. This is our disclaimer. Let us start by looking at what you will be able to do in this lecture. So our focus is on hydrocarbons, specifically the chemistry of benzene, I would say. So pay attention to the objective. The first one is to explain aromaticity. Aromaticity is a special property of some molecule like benzene, where electrons are shared in a way that makes the molecule extra stable. We will look at what a compound aromatic and why that is important in chemistry. Next, we will discuss how benzene is prepared. We will go through the main methods used to make benzene in the laboratory or industry, and will highlight the key steps and chemicals involved. As we move forward, keep in mind how these preparation methods connect to the unique stability of aromatic compound. So, topic which we will cover in today's class according to NCERT section 9.5.3 aromaticity, then section 9.5.4 preparation of benzene. Now, we start with the criteria for a compound to be aromatic in case of hydrocarbons and other heterocyclic compounds. Aromaticity is a special property that makes certain ring-shaped molecules unusually stable. We will break down the rules that define whether a compound is aromatic and see why these rules matter in chemistry. Starting by listing the main requirements for a molecule to be considered as aromatic. Notice, these are not just random rules. They help us to predict which compound will have unique stability and properties. We will go through each criteria step by step. First, the molecule must be cyclic. That means it needs to form a closed ring structure, not just a straight chain. For example, benzene, which is a classical example of aromatic compound, contains a six-membered atom ring, forming a perfect ring. Without a ring, aromaticity is not possible at all. Second, the ring must be planar. All the atoms in the ring have to lie in the same flat plane. This is important because it allows the electron to move freely around the ring. If the ring is twisted or puckered, the necessary electron overlap cannot happen. The third criteria is having a conjugated system. So this must be present. So there must be a continuous overlapping of orbitals around the ring, allowing electrons to delocalize. In simple terms, the electrons aren't stuck between just two atoms in a ring. They can move all the way around the ring, which increases stability by increasing the delocalization. Note, if any one of the criteria is not there in the compound, then your compound would be considered as non-aromatic. So above three criteria must be satisfied for a compound to be aromatic. Otherwise, it is non-aromatic. Now, the fourth rule, which is Huckel's rule. So compound will be only aromatic if it is cyclic and planar. So this is for sure, and it should have conjugation. Apart from that, for aromaticity, the compound should possess 4n plus 2 pi electrons in the ring, where n is a positive integer. Pi electrons are those found in double bond or lone pairs that can participate in delocalization. For example, benzene has 6 pi electrons. As I said, n is a positive integer, so it can be 0, 1, 2 and so on. So for n is equals to 0, you need 2 pi electrons. For n is equals to 1, you need 6 pi electrons. For n is equals to 2, you need 10 and so forth. This electron count is crucial. Only rings with this number of pi electrons is aromatic, and this is a counting rule that helps us quickly identify aromatic compound. Now, what about those which are not following 4n plus 2 pi electrons but are cyclic, planar and conjugated? For those, we have another set of compound which is anti-aromatic. So, anti-aromatic compound are actually less stable than regular rings. So, the electron count in count not only tells us if its compound is aromatic, but also if it is spatially unstable. So this wraps up the criteria for aromaticity. Remember, structure and electron count are both essential. So basically what is written here, if your compound is not following the first three rule, any of the first three rule, then it is non-aromatic. If it is following the third rule and not the fourth rule, then it is anti-aromatic. And if it is following all of those four rules, then it is aromatic. Now, we will discuss on aromatic compound with the help of benzene. So, if we consider benzene, so benzene is often used as the standard example when we talk about aromatic compound. It is a great starting point because its structure and properties are well understood and easy to illustrate. So, benzene is the simplest aromatic compound with the molecular formula C6H6. You can see its structure in the diagram. 6 carbon atoms form a ring, each bonded to one hydrogen atom. Notice the symmetry and the repeating pattern. So, this is key to its stability and aromatic nature. Then, we will analyze all the requirements for a compound to be aromatic on benzene. First, criteria is the molecule should be cyclic, means it should form a closed ring, and you can see here that benzene has a hexagonal ring structure, which means all 6 carbon atoms are connected in a loop. This ring is essential for spatial stability we see in aromatic compound. Next is looking closer, each of the 6 carbon atom in benzene is covalently bonded to each other and one hydrogen atom. This arrangement creates a stable repeating pattern around the ring. Continuing with the study of criteria for aromaticity of benzene, aromaticity is having the second criteria as planar nature. So all the carbon atom in the aromatic compound must be in one plane and each carbon uses sp2 hybridization. This type of hybridization means each carbon forms 3 sigma bond in a flat arrangement, leaving one unhybridized p orbital perpendicular to the plane. So planarity allows for the sidewise overlap of this p orbital. Taking a look at the diagram of benzene tells us that the p orbital on each carbon atom can overlap side by side because of their parallel nature, forming a continuous ring above and below the plane of the molecule. This overlap is essential for delocalization of electron, which is what gives aromatic compound their extra stability. So finally, it is essential to understand that planarity is required for delocalization of pi electron. If the molecule wasn't a flat, the p orbital couldn't overlap properly and the electrons wouldn't be able to move freely. This delocalization is what makes the compound aromatic so stable and unique. Remember, planarity and electron delocalization go hand in hand for aromaticity. Continuing with the next criteria, we have conjugated system. So you must have a conjugated system. Now, the pi bond here you can see that they were able to do a sidewise overlap, and this is allowing the pi electrons to move around. Notice in the diagram how the double bond can shift positions, showing this flexibility. This shifting is what allows the electron to be shared across the entire ring. Now let us focus on the idea of complete delocalization. This means that the pi electrons are not stuck just between two atoms but are spread out or delocalized over the whole ring structure. Here you can see from the image, pi electron clouds are present above and below. So due to the sidewise overlap, we are creating two sets of pi electron lobes above and below the ring. To summarize, a conjugated system in aromatic compound allows for both orientation of pi bonds and complete delocalization of electron, and these features are essential for the unique stability of aromatic molecules. Now, moving on to the fourth rule. Fourth rule is the Huckel rule. That means it should have 4n plus 2 pi electrons, where n is the whole number and pi electrons, as you know, are the electrons found in double bond within a ring structure. Now, the image shown shows benzene, a classical example of our aromatic compound we are studying so far. Now, let us pay attention how the benzene fits the rule. If you look at benzene, then it has 3 pi bonds. That means 6 pi electrons, where 3 pi bonds are donating 2 electrons each. Plugging this into Huckel rule gives us the value of n is equals to 1. So 4n plus 2 is equals to 6, then n is equals to 1. Now this calculation shows that the benzene meets the numerical requirement for aromaticity because n is now a positive integer here. Therefore, your benzene ring is following all of the four rules, including the Huckel rule. This confirms that your benzene is aromatic in nature. So, what we have observed so far, benzene follows all the four rules, including the planarity, then cyclic nature, conjugation, and Huckel rule. So, benzene is aromatic in nature. Now, we will look at some distinctive examples of aromatic compounds. So, starting with the first example, a compound that contains a carboanion. A carboanion is simply a carbon atom with a negative charge, which makes it highly reactive in most cases. However, in certain ring structure, this negative charge can actually help stabilize the molecule and make it aromatic, which we will look at a specific example to understand this better. The image illustrates resonance in the cyclopentadienyl anion. The negative charge and the lone pair of electrons on carbon 4 delocalize through the cyclic system. This involves the movement of electron forming a new double bond between carbon 5 and 4 and shifting the existing double bond between carbon 1 and 2, resulting in the negative charge moving to the carbon 3. This delocalization stabilizes the anion, making it aromatic and significantly more stable than a localized carbanion. First, let's check if the compound is cyclic. So, for a molecule to be aromatic, so we have seen the conjugation right now. Now, we are one by one considering the criteria for aromaticity. You can see here that the cyclopentadienyl is cyclic in nature, and therefore the first criteria is met. What about the second one? It should be planar. So, planarity means that all the atoms in the ring lie in the same flat plane. This is important because it allows the electron to overlap and delocalize around the ring, which is necessary for aromatic stability. So, here you can see in the first one that the C1 and C2, okay, and C3 and C5 all are sp2 hybridized. This means each of these carbons form 3 sigma bond has one unhybridized p orbital. These p orbital line up side by side, allowing for the delocalization of electrons above and below the plane of the ring. Your C4 is also sp2 hybridized. Okay, so remember, this is very, very important to remember that your C4 is also sp2 hybridized and your lone pair is lying in the pure p orbital. Okay, it is lying in the pure p orbital. Now, generally, carboanion are sp3 hybridized, but here it is sp2 hybridized. It is because your electrons want to remain in the p orbital so that they can take part in overall conjugation in the cyclopentadienyl. Now, why they are so eager to remain in the pure p orbital and delocalize? Because it helps them to stabilize the carbanion. So, remember this thing, your carbanion is sp3 in nature, but when it comes to aromatic compound, and if your pi electrons are required for the delocalization purpose, then they will do the sp2 hybridization so that the lone pairs can be on the pure p orbital and can be delocalized further. Now, continuing with this example, if you look, then the compound having the carbanion, so the cyclopentadienyl also has a complete conjugation. Okay, the third is for the complete conjugation and it has that. We have seen that in the starting part. Lastly, the fourth rule, it should follow the Huckel's rule. So, if you count the number of pi electrons in your cyclopentadienyl, then you can clearly say that it has 6 pi electrons. And if you just put it in the formula of Huckel rule, which is 4n plus 2 is equals to 6, then it will give you a value of 1 for n, which is a positive integer. That means your cyclopentadienyl anion is aromatic because it is following all the 4 rules. Got it? To recap, what we can say, the cyclopentadienyl is aromatic because it is planar, cyclic, fully conjugated and following the Huckel's rule. Now, moving on further, let us look at some remaining distinctive example of aromatic compound. So, the next one is carbocation. We have taken the example of cycloheptatrienyl cation. So, this is a 7-membered carbon ring with 3 double bond and positive charge. Notice how the positive charge is not just on one carbon, but it is actually delocalized over the ring, which is important for its stability. Take a look at the structure of the cycloheptatrienyl cation shown in the image. The ring is made up of 7 carbon atoms and the positive charge is spread out across the ring. This delocalization is what allows the compound to be aromatic even though it is a carbocation. The structure is often called tropylium ion. So, what we can say about the criterias? The first criteria is met because it is already cyclic. We have seen this, and it is a 7-membered ring at all. Next is we have to see whether the compound is planar or not. So, for aromaticity, all the atoms in the ring need to be in the same plane so that the p orbital can overlap. The cycloheptatrinyl cation is planar, which allows for this overlap and formation of a continuous ring of electrons. Now, coming on to the points, we can see here that the carbon 2 throughout the carbon 7 all are sp2 hybridized. This means that each of the carbon has one unhybridized p orbital that can participate in delocalization system. sp2 hybridization is important because it keeps the ring flat and allows for the necessary overlap of orbitals. Now, remember C1 is also sp2 hybridized. Even though it carries the positive charge, this means this leaves it with an empty p orbital, which is crucial for maintaining the continuous ring of overlapping p orbitals. This arrangement is what gives the cycloheptatrinyl cation its aromatic nature. Now, moving on further. Next, we have to look for complete conjugation in the carbocation, and we can clearly say that there is a complete conjugation. We have seen the image also in the previous part, right? So, this complete conjugation is essential for aromaticity as it allows for the delocalization of electron and hence the stability. Now, looking on to the fourth criteria. So, fourth one is Huckel's rule. Huckel's rule, we know that it states that your system should contain 4n plus 2 pi electrons in the conjugation where n is a whole number. In this case, the cycloheptatrinyl cation has 6 electrons in its conjugated system. If we set 4n plus 2 is equals to 6, we will find the value of n as 1, which is fitting the rule, and it confirms that your aromatic nature of your cycloheptatrinyl. Okay, so for summarization, what we can say that your cycloheptatrinyl is cyclic, planar, conjugated, and follows the Huckel's rule. Now, we will look at the third distinctive example of aromatic compound, which is a fused ring. These are aromatic compound where 2 or more rings share common carbon atoms. A classic example of this is naphthalene. This structure are more complex than simple benzene ring. So here is a naphthalene shown in the image. Naphthalene consists of 2 benzene rings fused together sharing 2 carbon atoms. This fused structure gives naphthalene unique chemical and physical properties to a single ring aromatics. Now, all 10 carbon atoms in the naphthalene are sp2 hybridized, which means each carbon atom forms 3 sigma bond and 1 unhybridized p orbital is remained in the carbon. This hybridization makes the molecule flat or planar, allowing for maximum overlap of p orbital and strong delocalization of electrons. Planarity is essential for aromatic stability. So, what we can say about naphthalene, that naphthalene is not only cyclic but also planar and hence conjugated at the same time. Conjugation means that there is a continuous overlap of p orbital around the ring, allowing the electrons to move freely. This delocalization of electron is what aromatic compound needs. And if you look at the Huckel rule, then it follows the Huckel rule as well, which is your pi electron should be in the count of 4n plus 2 pi and n should be a positive integer. So let's look at the structure. Total number of pi bonds are 5. Therefore, 10 electrons are possible as pi electrons. Now, if you just calculate 4n plus 2 is equals to 10, you will get n is equals to 2, which is the positive integer. Therefore, your compound is aromatic as it is cyclic, planar, conjugated and following the Huckel's rule. Now, we will shift our focus on anti-aromatic compound, a special category in the study of hydrocarbon. Anti-aromatic compounds are molecules that look like they could have been aromatic but actually have unique properties that make them unstable. We will use cyclopentadiene as our example to understand what makes a compound anti-aromatic. So let us start by looking at cyclopentadiene. Notice the structure shown here. It has 4-membered carbon ring, each carbon bonded to hydrogen atom. This structure helps us visualize the arrangement of atom in the cyclopentadiene, which is key for understanding its properties. Now, let us analyze all the criteria required for aromaticity. First, let us check if the cyclopentadiene is cyclic or not. So a cyclic compound means the atoms are connected in a closed loop in a ring. In cyclopentadiene, the 4 carbon atoms forms a rectangular ring, which satisfies this first requirement. So looking closer, each of the 4 carbon atom is in cyclopentadiene is covalently bonded in to 2 other carbon atom and 1 hydrogen atom. This closed ring structure is important because it allows us to consider the possibility of electron delocalization, which is a key feature in aromaticity. Next, let's see if the cyclopentadiene is planar or not. Planarity means all the carbon atoms lie in the same flat plane. This is important because only in a planar structure can the p orbital overlap sidewise, which is necessary for the electrons to move freely around the ring. So planarity allows for the sidewise overlap of p orbital, which is essential for the delocalization of pi electrons. And hence, you can say that your electrons are not only stuck between 2 carbon, but they are being delocalized over the entire ring, which is a requirement for anti-aromatic system. Continuing further. So what about conjugation? So if you look at the compound, in simpler terms, you can clearly say that the compound is completely conjugated because their all pi electrons are being not stuck to 2 atoms but are delocalized over the entire ring system. You can see here the delocalization, how it is occurring. The 1 and 4 double bond is moving to 1 and 2 double bond. Similarly, the 2 and 3 double bond is moving to 3 and 4 double bond, creating a new type of double bond configuration. Remember, this allows for the conjugation. Now next, the most important one. So it is following all of the 3 rules, but is it following the 4th rule, which is the Huckel's rule? Let's see. So for the Huckel rule, it should have a 4n plus 2 pi electron, where n is a positive integer. If you see at the cyclopentadiene, which is a 4-membered ring, you can see that it has 2 pi bonds, which means it has 4 pi electrons. If you calculate the n value from here, you will get it as half, which is not an integer, but it is a fraction. Okay. So you must remember that n must be an integer and not a fraction, and hence the given compound is anti-aromatic in nature because it is following all the 3 rules but not the Huckel's rule, because it has 4n pi electrons rather than 4n plus 2 pi electrons. Now if you sum it up, cyclopentadiene is cyclic, planar and conjugated, but it has 4n pi electrons instead of 4n plus 2 pi electron. This combination feature leads to a different classification, which is anti-aromatic. This means even though it looks similar to the aromatic compound, its electron count makes it unstable rather than the stability. Okay. Remember, anti-aromatic compound are less stable because of this electron arrangement. Now let us focus on non-aromatic compound. Non-aromatic compound are those that do not meet the criteria for aromaticity, the first 3 criteria itself. So we will explore them in detail. For that, we are taking the cyclopentadiene as our main example to understand what makes the compound non-aromatic. So here is your cyclopentadiene. Notice its ring structure in the diagram. 5 carbon atoms joined together. This is a classic example of cyclic hydrocarbon, but not a aromatic one. Why it is not aromatic? Let's see the criteria. First criteria is met. Your cyclopentadiene is cyclic in nature. Means the 5 carbon atoms are covalently bonded in a ring, creating a continuous loop. Continuing with the discussion. Next is your planarity. If you look at the image, here you can see that the carbon labeled as 1 has sp3 hybridization. Now the sp3 hybridization differentiates it from the aromatic compound like the cyclopentadiene, dienyl anion, as its presence breaks the continuous p orbital overlap required for aromaticity. So as a result of this sp3 hybridized carbon, all carbon will not lie in the same plane. Got it? And this lack of planarity can prevent the molecule from having the necessary overlap of p orbital for aromaticity. Therefore, what we can conclude that C1 is sp3 hybridized, making it out of the plane in the ring. And this is the most important criteria for the delocalization of electron. Therefore, what we can say finally, that the compound is not following the second criteria in the start only, and hence it is non-aromatic. Okay. So it is forming a ring, but due to the sp3 hybridization of carbon, it is now not a part of the ring, removing the complete conjugation from the ring and hence making the compound non-aromatic. Now moving on further. Next, we have a table which will help us to differentiate between aromatic, anti-aromatic, and non-aromatic compound. These categories are important in understanding how certain molecules behave, especially in organic chemistry. This table summarizes key differences between aromatic, anti-aromatic, and non-aromatic compounds. Aromatic and anti-aromatic compound are both cyclic, planar, and have continuous p orbital conjugation, but differ in their pi electron count, which is 4n plus 2 pi for aromatic and 4n pi for anti-aromatic. Due to this, the stability of aromatic compounds are extremely high and anti-aromatic compounds are extremely low. The non-aromatic compound fails at least one of the first three criteria, which is not cyclic, or whether it is not planar, or whether it is not fully conjugated. Now, due to this, your pi electrons are not delocalized and they are non-aromatic in nature. Their stability is intermediate. So, what you can say about the whole series, the most stable is the aromatic, then comes your non-aromatic, and lastly the least stable is anti-aromatic. Moving on to the preparation of benzene. So benzene can be prepared in the laboratory through several methods. First one, the most common method for preparing benzene is cyclic polymerization of ethyne. Polymerization means joining small molecules together to make a larger one, and cyclic means the final product forms a ring structure. Ethyne is known as acetylene also, so this name can also be used instead of ethyne. We'll see how it can be turned into benzene. Second one is decarboxylation of aromatic compound. Decarboxylation means removing a carbon dioxide from the molecule. Aromatic compounds are compounds that contain a benzene ring and a carboxylic acid. From them, if you remove CO2, we can get benzene there. The last one is reduction of phenol. So reduction in chemistry means gaining hydrogen or losing oxygen. Phenol is a compound with a benzene ring and an OH group. By reducing the phenol, we can convert it into benzene. Starting with the first one, which is polymerization of ethyne. So this process is especially important because in industry, it helps us to understand how simple molecule can combine to form more complex one like benzene. Ethyne or acetylene in a simple hydrocarbon with the molecular formula C2H2. In cyclic polymerization, three ethyne molecules react together to form a ring structure, which is benzene. This is a great example of how a small linear molecule can create a stable ring. So here you can see the chemical reaction. Three molecules of ethyne, they are combining together to form one molecule of benzene in presence of red hot iron tube and 873 Kelvin temperature. Atoms are rearranged to create a 6-membered ring of benzene. Now, to summarize this reaction, three ethyne molecules join together to make one molecule benzene. This shows us how multiple molecules can combine to form a large, more complex structure. Further, it is important to note that this reaction only happens under specific conditions such as high temperature. The right conditions are necessary to break and form the chemical bond needed to create benzene. Continuing further, now we look at the method known as decarboxylation of aromatic compound. This process is important for preparing hydrocarbon, specifically benzene, from aromatic compound. Let's see how this method works step by step. So, you will take first of all sodium salt of benzoic acid in this method. Benzoic acid is an aromatic compound, aromatic acid, and converting it to its sodium salt makes it more reactive for the next step. Remember, sodium salt are often used in organic reaction to make the process smoother. So, let's see what happens when we heat the sodium salt of benzoic acid with soda lime. Soda lime is a mixture of sodium hydroxide and calcium oxide. We have seen this reaction previously also. When we heat this together, the reaction removes the carboxyl group from the benzoic acid, producing benzene as the main product. This is a classical example of decarboxylation where a carbon dioxide molecule is removed from the compound. So here you can see the chemical equation as well. You can see that the sodium salt of benzoic acid is heated with the sodium hydroxide at higher temperature with calcium oxide, which is basically together named as soda lime. Now, next what we will do, if we heat it, we'll get benzene and the sodium carbonate. Got it? I hope this is clear to you. Next, we'll study the reduction of phenol. In this process, we start with the phenol vapors, which are simply phenol in a gaseous state. This vapor are passed over heated zinc dust. It is important to note that the phenol is an organic compound with a benzene ring bonded to a hydroxyl group. we will see what happens next when zinc is involved. So zinc acts as an reducing agent. This means zinc helps us to remove oxygen from phenol, effectively converting it into benzene, which is a simpler hydrocarbon with just a benzene ring and no extra group. You can see the chemical equation here. Remember, the reducing agent like zinc are crucial because they donate electrons to remove oxygen, leading to the formation of hydrocarbon from more complex molecules. Now we will see a question here. Let us clear the concept by practicing a question. Here you are provided with 3 structures and you have to tell why they are non-aromatic in nature. So, if you look at the solution before that, this question is about aromaticity in organic compound. We are asked to explain why the system are shown in the image are non-aromatic. Aromaticity is a special stability found in some ring-shaped molecules, and understanding why a compound is or isn't aromatic is important about for both chemistry, especially when we talk about electron delocalization and molecular stability. If we focus on the structure labeled as 1, take a look at the structure shown here. We will analyze its features step by step to see why it doesn't qualify as aromatic. This ring contains a carbon atom that is sp3 hybridized. In simpler terms, sp3 hybridization means the carbon form 4 single bond and a tetrahedral structure. This disrupts the planarity of the structure needed for aromaticity because all atoms in aromatic ring must be in the same plane for the electron to move freely around the ring. Even though the compound has 6 pi electrons, which is the right number of aromaticity according to Huckel's rule, it is not enough by itself. Pi electrons are the electrons found in double bond, and having 6 of them is a good sign. But other condition must also be met. Next, due to this sp3 hybridization, there is a partial conjugation, and that partial conjugation is represented in the image as well, and hence it lacks the ability to do the complete conjugation through the ring, making it unable to be a aromatic system. So what we can say, due to its failure of following the first 3 rules, it is non-aromatic compound. Continuing further, next what we have? Next we have this 5-membered ring where there are 2 pi bonds. Take a look at the structure. We will break down its feature to see why it doesn't qualify as aromatic. Pay attention to the type of atoms and bond present in the ring. Notice the ring contains a carbon atom that is sp3 hybridized. In simpler terms, the sp3 carbon has 4 single bonds and it is not flat like the rest of the ring. This disrupts the planarity or flatness of the molecule, which is essential for aromaticity. So, the presence of this sp3 carbon makes the whole ring non-planar. Next, sp3 hybridized carbon. The electron in the ring, due to this sp3 hybridized carbon, the electron in the ring cannot move freely around the entire structure. This means that there is no complete conjugation. Conjugation is when p orbital overlap continuously around the ring, allowing the electron to delocalize. Without this, the compound cannot be aromatic. After that, we can finally sum up. The key reason for the compound to be non-aromatic is that it has a sp3 hybridized carbon, which breaks both planarity and conjugation at the same time. So the given compound does not meet the criteria for aromaticity. Remember, for a compound to be aromatic, it must be cyclic, planar, fully conjugated, and must follow the Huckel's rule. Then moving on to the last compound. So what was the last compound? It is a 8-membered ring, which is labeled as 3 in the question. So we will look at the features of the given compound one by one. For the given compound, if you see, the number of pi electrons is 8. Now, the pi electrons are expected to be in conjugation, right? So this is true. If you look at the structure, there is a conjugation possible due to double single. You can see alternate double single bonds. But in actual, the compound is non-planar in nature. It has a tub-shaped structure. This is given here in the lower part. Now, why it is forming a tub-shaped structure, not a planar one? Because if it would have been planar, then there would be the met of the first 3 criteria for the given compound. But the 4th criteria won't be followed because the number of pi electrons is equals to 4n pi and not 4n plus 2 pi. Due to this, the compound can be anti-aromatic. To avoid this anti-aromaticity, rather than going into the anti-aromatic criteria, it makes it unplanar, non-planar. And due to this non-planar nature, it will be non-aromatic, because you know that anti-aromatic compound are less stable than non-aromatic. So your compound is taking such a configuration so that it can go from anti-aromatic to non-aromatic, which is tub shape. So the given compound, due to its lack of planarity, it is not conjugated fully over the ring, and hence the compound is non-aromatic. Let us summarize our today's class with a short summary. So we studied the criteria for aromaticity in today's class mostly. So we'll break that down, what makes a compound aromatic, and then look at how we classify them based on their electrons and properties. First one is cyclic. So the compound should form a cyclic ring for the complete conjugation. Next is it should have a planar structure. So the ring need to be like a sheet of paper. This allows the electron to move freely above and below the ring, which is important for aromaticity. Then next one is conjugated p orbital, and this is only possible when all your p orbitals are parallel to each other. Now this is the basic criteria for aromaticity, but the most important one is the basis of pi electrons. So on the basis of pi electrons, if it is having a 4n plus 2 pi system for electron, then it is aromatic. Okay, here n can be only a positive integer, so it can be 0, 1, 2. For example, benzene has 6 pi electron. This means here, in that case, n will be equals to 1. Next, if it is having a 4n pi electron, that means your 4n plus 2 is giving you a n value of fraction. Then in that case, your compound will be anti-aromatic in nature. Got it? Now, if the compound is not following the first 3 above criteria, means these 3, then it is non-aromatic. So what we can say again, if I just summarize it all, if your compound is following this first 3 rule and not the 4th rule, then it is anti-aromatic. If it is following all 4 rules, then it is aromatic. And if it is not following the first 3 rules itself, then it is non-aromatic. Moving on further, then we talked about the properties. So aromatic compounds are highly stable and have a low energy. Okay, whereas the anti-aromatic compounds are highly unstable and they have a high energy. And the non-aromatic compound have a intermediate stability between the aromatic compound and the anti-aromatic compound. So this wraps up our overview of aromaticity. Moving further, we saw about benzene. So benzene, which is a classical example of an aromatic compound, they are special groups of hydrocarbon with unique stability and properties. We will see that what makes the benzene compound aromatic and then explore how it is prepared in the lab. First of all, it satisfies all the criteria for aromaticity. It is cyclic, it is planar, and it is conjugated. At the last, it has 6 pi electrons, which gives you the n value as 1. Therefore, it follows all the 4 rules required for a compound to be aromatic. Therefore, your benzene ring is aromatic in nature. Then we talked about the preparatory methods for benzene, which includes decarboxylation, cyclic polymerization, and reduction. If I talk about the cyclic polymerization, then we started with the ethine. So ethine under high temperature and pressure can undergo cyclic polymerization to form benzene. Next is decarboxylation. So if you do the decarboxylation for sodium salt of benzoic acid, then it can be converted into benzene by removal of carbon dioxide from the compound. After that, we have the phenols reduction. So if you do the reduction of phenol in the presence of zinc dust, then it will lose oxygen atom and it will be converted into benzene, which is again a preparatory method used in the industries for the preparation of benzene. This was all for today's lecture. Thank you for joining the session. I hope you enjoyed it.